Hi, and welcome everyone. How's everyone doing today? My name is Guy Royse, and my talk today is called Understanding Probabilistic Data Structures, which is very possibly a thing you haven't heard of. But more importantly, it's with 112,092 UFO sightings. That's an oddly specific number, isn't it? Just to sort of level set here, I'm going to try and be monitoring public chat while we're going here. So if you have a question in the midst of things, you can leave it in the Q&A using the question mechanism. If you say something in chat, I'm going to try and keep my eyes on that, and I'll answer it as it makes sense. And I realize there's lag. I stream. Don't worry. It'll all be fine. I'll get to your question eventually one way or another. So, and if we can't do it in this context, we'll just do it on Twitter later. No problem. So, I already introduced myself, but I'm a developer advocate at Redis Labs, which means that I go to events like this and give talks and mention Redis Labs while I'm at it. So I'm mentioning Redis Labs now. Go check our stuff out. Redis is cool. You're probably using it already. You can follow me on Twitter. All the code that I'm going to have or may not have time to show here is up on GitHub at that URL. And if you want to read outdated blog posts, you can go to guy.dev. The best part about having guy.dev is just having guy.dev. It's like it's a 3-letter domain name. How many people get to have that, right? So anyhow, 112,092. So that's an oddly specific number, isn't it? Well, as it turns out, it happens to be the number of UFO sightings that I have access to. There's a data set of UFO sightings on data.world. This wonderful man by the name of Timothy Renner screen scraped the National UFO Reporting Center's website to gather all of these sightings and put it up for everyone to use. And it covers all the UFO sightings that they have in their database since like about 1950 in the United States. And it's just great data. You go in there and you look at these UFO sightings, and it's just fantastic stuff. They store a sort of a summary of the data, of the UFO sighting. This one is 3 saucer-shaped ships. I know that's sort of like Sue sells seashells by the seashore. Kind of hard to say. High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. Sounds like a UFO sighting to me. This happened near Salem, Oregon. And this happened on September the 15th of 1950. So this is an older sighting. They have the shape, disc or, some cigar or light. There's lots of options for the shape. How long it was, a link back to the original stuff, the original report, the full text of the report, not just the summary. And if you get a chance to go browsing through this data, some of these are just absolutely delightful to read. They're so much fun. And Tim actually took the city and state and got the latitude and longitude of the city and state as well to put in here, so he could plot it out and find out where all the UFO sightings were happening. And what he found was that they were all within 50 miles of a U.S. airbase. So, shocker. So that's the data we're going to play with. And I thought this would be fun data to explore probabilistic data structures with. It's a little bit whimsical, but it makes it a little more fun. And they're kind of unknown, right? Kind of like probabilistic data structures. Because you're probably wondering, what's a probabilistic data structure? Well, that's a good question. I wondered this when I first got into this topic. I had not heard of them. And it turns out you're not terribly alone if you aren't familiar with probabilistic data structures. Back in December, when I was putting this talk together, I did a quick survey so that I could have the slide, right? Asking who had heard of probabilistic data structures, and nearly 60% of developers had never even heard of them. So that's the majority, right? About a fifth had heard the term but didn't know what they were. I don't know what percentage of them had heard the term in this question. That would be something us literal-minded developers might do. But so we're already in 80% of developers have heard of them at best. The other 20% were split between knowing what they were and had actually used them. So 1 out of 10 developers has actually used a probabilistic data structure. So if you don't know what these are, you're in the perfect place, right? That's exactly where you should be. This is where everyone is at. So it's all good. Don't worry about it. But to explain what a probabilistic data structure is, I first want to talk about sort of their evil opposite, the reptilian to their grays. That'd be the deterministic data structure. And deterministic data structures are, well, they're the ones you use all the time. You actually know what these are. You've used linked lists, and you've used arrays, and you've used trees and stacks and hash tables. What makes a deterministic data structure deterministic is that it does what you expect it to do every time. So if I add something to a hash table and then go pull it out, I expect to find it there. If I add something else to a hash table and go get the previous thing, I still expect to find the previous thing there. It's deterministic what happens when you use them. There's no chance of them not doing what you expect them to do. Well, they might do what you don't expect them to do, but that'll be your fault, not the data structure's fault. And so you've used these a million times. I'm going to dive into detail on how one particular deterministic data structure works, and those are hash tables. And the reason I'm going to do that is because it uses a pattern that you see in a lot of probabilistic data structures. So this is the hash table. If you're not familiar with hash tables, you are. You just don't know that they're called that. A hash table is a key value pair. So here we have that same data that we were looking at earlier, but in a hash table, right? It's in Java, these are your hash maps. In Python, these are dictionaries. In JavaScript, it's, well, everything. But you've used these before. You put in a key of city, and you set the value of Salem. You can request it by that key. You get Salem back out. Key value store. And the reason they're called hash functions is because, or hash tables, is because they use hash functions. A hash function is something that will take a random seed number and data. So when you go to use a hash function, you give it a seed, and you use that seed repeatedly. And then you give it data. Here I've got 6 bytes, which is a UTF-8 encoded Scully for those X-Files fans out there. And so if you give it that data and you give it that seed, it will flatten it to a fixed width number. In this case, a 32-bit number. And it doesn't care how big that data is. It can be a gigabyte. It can be 10 bytes. It doesn't matter. It will flatten that out to a statistically unique number. And when I talk about hash functions here, I'm not talking about cryptographic hash functions. Cryptographic hash functions are slower, and have security mechanisms. This is more like a murmur hash is the one I like to use, where it's fast but generates things that are statistically unique, but they don't have any extra security features. The speed and uniqueness are what we care about here. But so a hashing function basically takes data and boils it down to a single signature. And then to use a hash table, what we do is we take the key of what we want to store. So here we want to put city. We want to put the value of Salem in the key of city. So we specify city. We run city through our hash function with our seed, and we get a number, big 32-bit number. But our hash table isn't 32 bits wide, right? That'd be kind of crazy, right? That'd be, billion entries. Our hash table here is only got 10 values in it. It's an array with a length of 10. And so we need to take that 32-bit key and compress it down to a smaller value that we can use as an index. And so since we have 10 items in our list here, in our array, in our hash table, we do a modulus 10. If we had 20, we'd do a modulus 20. If we had 5, we'd do a modulus 5. And that gives us an index, which probably won't be unique, but will be unique enough. And there's a solution to that problem, which we'll get into here real soon. And we just, so this, presumably this hash function spits out a number that ends in 1. And so we shove it here in number 1. And then if we go to add something else, we go through that same process. We're going to add the state, Oregon. And that ends up giving us a 4, so we put it in position 4. But sometimes you'll get a collision. We got an index of 0 through 9 here. It's really likely we're going to get a collision. And so what we do in that scenario is that we don't just shove the value in there. What we're actually doing, this is not an array of strings. This is an array of linked lists. And so what we're really doing is when we add to this array, we add to the linked list. And that linked list stores not just the value, but also the key. And so right here where it says Salem, it's actually shape Salem, or city Salem. And here we're storing shape disk. And so what we do is we just append to that linked list. And so we have a linked list of values. So we can store both of those values. When we go to read it, what we do is we go to the linked list and we walk it until our key matches the value. And if the key doesn't match the value, then it's not in the hash table. And so this is how hash tables work. They're actually pretty clever if you think about it. I'm glad someone a long time ago thought of this so that I didn't have to. Always grateful for that. And one of the things that we're doing here with the hash table in particular, but in deterministic data structures in general, is we're making trade-offs for performance versus efficiency, space efficiency versus time efficiency. So modifying a hash table for the most part and reading it is, not counting the walking of the linked list, is a constant time operation. That hashing is a constant time operation. The array access is a constant time operation. The only part that's not is the walking of the linked list. But it's got a lot of empty space in it. You've got this array, but you haven't used all of it. And so it's sacrificing some space to make things faster and more convenient. And correspondingly, a linked list is super compact. It has just what it needs in it. It's very space efficient. But if you want to find something in a linked list, you have to walk that entire linked list. And so it tends to be time inefficient. And so you're making these time and space complexity trade-offs when you're selecting your probabilistic data structures. But that's actually a slight lie, because you're actually making these trade-offs within themselves sometimes. So these aren't always in opposition. For example, the linked list is inefficient to traverse, but it's actually very cheap to modify. Removing an item from a linked list or appending something to the end is very inexpensive. And so when you select your data structures, you're making those trade-offs even within that same domain of time or the domain of space. And this is where we get to probabilistic data structures. There's a third thing that you can trade off against, and that's accuracy. You can make data structures that lie to you, right? That sounds crazy, right? It's like, well, there's a probability that they'll lie. That's why they're probabilistic. And so what you're doing is you're saying, well, can I save a bunch of time and space? Can I make something that's really fast and really compact if it lies to me 0.5% of the time? Is that worth it? That might be worth it. If you've got 1,000 entries, probably not worth it. The space isn't that big anyhow. If you've got 1 billion entries, that's 0.5% inaccuracy could very well be a reasonable trade-off. If you have, say, 1 million usernames and you want to check and see if the username's taken or not, if we say that username's taken when it's not, that's okay, as long as we're not doing that half the time. If we're only doing that, say, 1% of the time, then that user just never gets used. But the application still works fine and it works faster. And so these are trade-offs, right? You make that accuracy trade-off. And we've actually got lots of mundane experience with this without even realizing it. If you've ever used a JPEG, and that would be everyone, right? You've all browsed the web and seen a JPEG. JPEGs have a lossy compression, which means that we compress them down to the point where we lose some of that data when we decompress it. But it doesn't matter, because if you look at like one of these blue pixels here in this picture, it's probably the wrong shade of blue, but no one cares. You can't see it. You can't tell. And so it's lossy, it's inaccurate, it's probabilistic, but it's good enough. And that's the trade-off that we're making here. Probabilistic data structures, particularly the ones we're going to look at today, can be thought of as sets that have peculiar properties. So if you think about a set in terms of like a set theory in mathematics, you can add or remove things to sets. You can get the intersections and the unions and the differences. You can test for membership. You can test for cardinality, or you can check the cardinality of a set. And these are all things you can do. Probabilistic data structures look like this, but they often have some of these capabilities removed. Like maybe you can add things to the set, but you can't remove them. And then you can only check for membership. Or maybe you can add and then do like unions, but that's it. But you can only test the cardinality. And so you have restrictions on the types of operations you can do, but they, for the most part, behave like sets. And so some of the probabilistic data structures optimized around a particular capability. We're going to look at membership. A probabilistic data structure that is keyed around membership is asking the question, is this thing in the set or not? right? So here we have in our set a star, a square, a circle, and a triangle, which are totally not the shapes that are in the Redis logo. And we're asking the question, is the square in the set? Yes. Yes, it is. Is the nonagon in the set? No. And what is a nonagon anyhow? It's got 9 sides. That's what a nonagon is. So we can ask that. Is this a member of the set or not? We can also ask for cardinality. This is just saying how many unique things are in the set. This set has a star, a square, a circle, and a triangle. So it's got 4 unique things. It's got a cardinality of 4. If we remove the triangle, it would have a cardinality of 3. If we added the aforementioned nonagon, it would then have a cardinality of 5. So just that's how many unique things are in the set. Frequency is can be confused with cardinality because it's counting. We're still counting here. But what we're doing here is we're counting how many of the things are in a set as opposed to how many unique things are in a set. So we're saying how many stars are in the set, how many squares are in the set, how many triangles are in the set. And so this lets us count set items. And something you can derive from frequency is rank. This is ordering your set. Probabilistic data structures that do rank often don't count accurately, but they count accurately enough to rank accurately. So that's the idea, right? So I don't need to know that there are 6 circles and 4 squares to know that there are more circles than there are squares. I just need to know that one number needs to be bigger than the other. And so rank is where we go through and we put those items in a set in a particular order. And of course, we can compare sets to see how similar they are. And one of the probabilistic data structures we're going to look at today, Minhash, which is, I suppose, not strictly speaking a probabilistic data structure, but it kind of is. It uses probabilistic mechanisms to compare documents. But you can compare different sets. You know, we got a set here that's got a star, one that doesn't. It's missing the star. And how similar are these sets? How can we compare them? And we'll get into detail on that in a moment. When it comes to selecting probabilistic data structures, there are a lot of choices. I'm going to talk about the 3 that are highlighted in blue here: Bloom filters, Heavy Keeper, and Minhash today. The ones in gray are also worth checking out. The ones with the little red dagger next to them are things that are available as part of Redis as well, so that you can just use the Redis probabilistic data structure instead of coding your own or using a library. And for the Bloom filter and the Heavy Keeper, I'll show how to use those with Redis as well. The one with the double dagger here, HyperLogLog, is part of Redis core, whereas the rest are part of Redis Bloom, which is a module that extends Redis with probabilistic data structures. And so we got Bloom filter and Cuckoo filter for membership. They're pretty comparable. Cuckoo filter is a little more capable. You can remove items from it as well as adding. HyperLogLog lets you count billions of items, get the cardinality of sets with billions of unique items, but only takes up 12 bytes or 12 kilobytes, which I think is kind of amazing. Count Sketch and Count Min Sketch are for frequency. We're going to go into Heavy Keeper for rank. Heavy Keeper is actually fairly sophisticated, but very interesting. And Minhash is for comparing documents. So let's look at Bloom filter first. A Bloom filter is a set, and it tests for membership. So you can do 2 things. You can add things to a Bloom filter, and you can check for membership. My example I gave at the beginning of is the username taken or not is a great example of when you could use a Bloom filter. A Bloom filter will answer no, it is not in the set, or probably it is. So in the case of usernames, it would say no, that username is not taken, or it would say yeah, that username's probably taken. It can't tell you it is taken definitively, but it can tell you probably. Bloom filters have a fixed size. So when you create one, you're creating a Bloom filter that's set up to store, say, 10,000 items. Then that's how many you want to put in there. Don't exceed that size because it'll fill up and it will start giving you probably as the answer all the time. You'll start getting a lot of false positives. And it's constant time. Goes through hash, checks a bit array. That's how they work. Speaking of hashes and bit arrays, here's the parts of a Bloom filter. So right here we have our hash functions with seeds. I picked 3 primarily because it fits on the screen. You could have more or less, just depends on what you're trying to do. And you've got this bit array that's a fixed width. It's all the bits that make up the filter. The wider it is, the more things you can store in that Bloom filter. The shorter it is, the fewer things. And the more hash functions you have, the more this Bloom filter will fill up faster. So if you have more hash functions, you want to have a wider bit array. To use a Bloom filter, we're going to add UFO sightings to make sure that we've seen them before. Now, we're trying to catalog a database of UFO sightings. If we've seen them before, we don't need to add them a second time. And so here we're adding Megatron in the bushes. This is a great story of a couple of young men who were driving along the highway in Arizona and decided to take a pit stop on the side of the road to take care of business, and heard a weird noise in the bushes, which sounded like the Transformers transforming from the old 80s cartoon with the whole, the Transformer sound effect that they make in the movie when they transform. They heard that in the bushes. And so they freaked out and headed down the road in their car, and apparently were chased by lights for, probably 75 kilometers as they're heading west away from their site. So great hysterical story. Go check it out. But what we can do is we take Megatron in the bushes and we can run it through these hash functions, just like we did the keys for the hash table. And this is going to generate some numbers, some 32-bit numbers. And just like with the hash table, we're going to modulus them with the width of, in this case, our bit array. In the case of the hash table, it was the length of our array of linked lists. And we're going to modulus that with that length and get an index. And so here we get, a hypothetical 5, 0, and 6. And so we put ones in all those places. So now Megatron in the bushes is in the Bloom filter. The string is gone. It's been hashed away into just 3 bits in this array. If we want to read it, we go through exactly the same process and say, is Megatron in the bushes in the Bloom filter or not? We hash the values, we get the numbers, we look at the indexes and say, well, they're all ones, so yes, probably. If we got back a 0, then it would be no, definitively no. And we know that because if it was set to a 0, if there's a 0, nothing is ever set to a 0, which means nothing was added to touch that. So that means definitively no. But since we can add multiple things to a Bloom filter, and sometimes they can collide, we can't know definitively yes. So here we're adding another UFO sighting. I seen a UFO when I was about 13 years old, bad English and all uppercase from the original story. And what we've had here, we did the same process, but we got a collision on position 6 right here. But that's fine, because when we go to read it, we get all ones. And so it's there. We're good. We go to read Megatron in the bushes, we get all ones. It's there. So that's good. But the collision happens, but it doesn't impact us. And this is why we have multiple hash functions, because the collisions become less impactful. But the more hash functions we have, the wider our array needs to be. What will happen sometimes, though, is you'll get a total collision. Here we have investigators from the Bigfoot Field Researchers Organization observing a glowing green-blue sphere. And in this case, all of the numbers, all the indexes we generate are already filled with ones. And so we haven't modified the state of the filter. And so is this in the Bloom filter or not? Well, that's almost a philosophical question. If we look at it from point of view of I added it and then I checked, then yes, it is. But if I hadn't added it and I checked, it would still say it is. And so, right, this is the false positives that you can get with Bloom filters. And you can see how that once this fills up with ones, it just always is going to say probably. So you might be wondering how to determine how wide to make your Bloom filter and how many hash functions to use. Just use this easy math. It's actually not that hard. There's 2 things. You know how many items you want to put in it, and you guess at the number of bits. You solve for K. Using K, you solve for P. And P will give you a false positive rate. If that rate is acceptable, great. If it's not, increase or decrease your bit width. And then you can sort of hone in on the size. Another option, of course, is just use Redis. We have the bf.reserve, and we just tell it the acceptable error rate. So here I want to create a Bloom filter with a capacity of 100 that has an error rate of 0.5%. And I'm going to make a key called UFO shapes. To add to it, I just use bf add or bf multiple add or bf mad. And to A check for existence, I call BF exists or BFM exists for multiple exists. And it will return ones and zeros accordingly. So it's very easy to use in Redis. Minhash, and I'm looking at my clock here and I'm like, sorry, folks, I'm not going to be able to do the demo, but we'll be fine. Minhash is not part of Redis, but it's really interesting. It lets you compare documents to see how similar they are. You might use that to say, have I indexed this document before? Or perhaps look for plagiarism. Or see if a document has changed enough to justify re-indexing it. And so it determines set similarity between documents. But to determine set similarity between documents, we need to understand set similarity. And we could determine set similarity by looking at using Jacquard similarity. Jacquard similarity is it's actually a pretty simple calculation. It's the cardinality of the intersection of two sets divided by the cardinality of the union of those sets. And so here we've got Scalder and Molly. Scalder has a list of states in the United States that he's seen UFOs in. And Molly has seen UFOs in certain states as well. And the union of that set is 10. The intersection is New Mexico and Ohio. So Area 51 and Hangar 18. So that seems legit. And so we do 2 divided by 10, and we get that these sets are 20% similar. This is a very easy calculation to do. But if we do that calculation against a document, well, how do we turn a document into a set? First instinct might be just take all the words and they make up the set, right? But that doesn't work because we're using all the same words. And so they're going to be the same, right? The similarity is going to be heavy. It's just going to tell us that this document was written in the same language as the other document. And so you can solve that problem by shingling your documents and turning them into sets that way. Shingling is where you take a trigram, a group of 3 words, and you add it to your, that becomes the first element in your set. And then you do an overlapped next 3 words and next 3 words to build up a set of overlapping or shingled, like shingles on a house, trigrams that make up a set. And then once you have that shingled set, then you can do Jacquard similarity against those shingled sets. And so here we've got Scalder's report of a UFO sighting, and we got Molly's report of a UFO sighting. And Skinner wants to see if they are telling a similar story or not. We do the math here and get an intersection of 7, a union of 11, and they are roughly 2/3 similar. So Skinner says they're seeing similar things from a different perspective, and he's happy that they're doing their jobs. But there's a flaw in this process too, which is that we're doing set comparisons on strings, and that is super slow. And not only are we doing set comparisons on strings against 2 documents, which wouldn't be that big of a deal, but these documents could be big, right? These don't have to be, 10 lines. They could be, they could be 100-page documents. And you may have a bunch of documents you all want to compare against each other. And so Minhash is where you take these shingled documents, these shingled sets, and turn them into a set of numbers that you can compare instead. So in this case, we've got Scalder's report, and we take every entry in that shingled document right here, and we run it through a hash function. And we have a collection of hash functions. Again, I picked 3 because it fits on the screen. And so we notice 2 in the first one becomes 325. And notice 2R becomes 489. And 2R left becomes 646, et cetera, et cetera. And we do that for each hash. And so we end up with 3 sets of hashed values for that set of shingled trigrams. We then take the minimum number and create a new set. And we end up with a set equal to the number of hashing functions we use. So we use 3 hashing functions. We get 3 numbers out here. We do the same thing for Molly, and we end up with 2 sets of 3 numbers. Here we've got 233, 143, and 102 for Scalder, and similar numbers for Molly. We do the Jacquard similarity, and we end up with a intersection of 2, union of 4. These are 50% similar now when we use Minhash. So that's how Minhash works. You might be looking at this and thinking Minhash wasn't very accurate. The other one gave me a much more precise number, and that's a feature of the fact that I only use 3 hashes. By 3 hashes, by definition, you're going to get 0, 0.25, 0.5, 0.75, and 1 as their similarities. Those are the only options. They're either completely the same, different, or somewhere in between. And that's just because we use 3 hashes. If we want more resolution, we use more hashes. So that's Minhash. I think Minhash is particularly neat. Let's look at the last structure, top K, which is actually heavy keeper and a min heap. But min heaps aren't probabilistic, so we won't go into detail on those. Top K is all about ranking. It ranks the top K items. When I first saw this, I'm like, I don't have a strong statistics background, so I always think of N instead of K. So this is really the top N items in my brain. But K, for the arbitrary value K, how many items? Just like the top 5 most clickbaity, headlines of all time, right? It's that kind of top 5, that kind of top K. And its heavy keeper is all about ranking top K items of a set. You add things to it, and then you can ask it, is this in the top K? What's its order in the top K? Give me the top K items. It's got 2 parts. I mentioned those already, the min heap and the heavy keeper. The heavy keeper is particularly interesting. And again, it does this hashing thing to get indexes. So our heavy keeper has a collection of hash functions. It's got associated with each of those hash functions is an array, just like with the hash table, just like with the Bloom filter. But this array contains buckets that have the hash value that was used, that 32-bit number, and a count. And so it's a little bit different. And the way it works is, here's our brand new heavy keeper. All the hashes are null. All the counts are 0. And when we go to add something to it, we're going to add the word object. We're going to keep track of, we're going to look for the most common UFO shapes here. Object is one of the most common shapes. And so we take the word object, we run it through our hashing functions. We get our signature, we get our hash value, our 32-bit number. We modulus it with the width to get an index. So here we get 212. And then what we do is we shove the hash value that we computed and we increment the count. We come in here, hey, this is 0 and null, so let's fill it up. This object came in here once, and we do that for each hash function. So we've got those 3 values in there now. If we add object a second time, it does that same computation, looks at index 2 and finds that there is something there already and that the hashes are the same. Since the hashes are the same, it just increments the counter. And it does this in all three rows here. And if we want to query the count, we just reverse this process. We go in, we look at all the rows, get those indexes, look at the rows, and look at our counts, and we can pick the biggest out of all 3 of them. Right now, they're all 2s, so it's 2. The count's still good. If we add something with a different value, let's say light, this is another popular UFO shape, then it works the same way, right? Here we run into a null, so we put the hash value in there in a 1. Here we have a null, we put the hash value in a 1. But down here, we've got a collision. Position 2, index 2, has a hash that doesn't match the hash that we computed for light. So what do we do in this scenario? Do we delete it and replace it? Or what, right? Yeah, deterministic data structure plus special. That's a good summary. That's a good summary there. So what do we do in this scenario where we have this collision? Well, there's a chance that we will decrement it. It'll go from a 2 to a 1. And if it goes all the way to 0, then we remove it. And that probability is determined by using a magic number B, which is greater than 1, but about 1. So like 1.05 or 1.02 or 1.01. And then we take that to the negative power, the power of the negative count. So if our count is 2, that'd be negative 2. So since these are negative numbers, that's going to get smaller. So 1.05 to the power of negative 2 gives us 0.907. So we have a 90.7% chance of decay. Now you can, if this number gets big, if there were 1,000 items here, this would be a very tiny number, and the probability of decay diminishes. And this is how it hangs on to heavy things. As the count grows, it's less likely to let go of them. It's a heavy keeper. It keeps the heavy things. Whereas if the numbers are small, they're likely to be decremented. So in this case, I'm going to roll the dice and say that, yes, they are indeed being decremented. And so what we do is we decrement the count in this value, but we don't change the hash. So it still contains the previous hash. It's just smaller. If this gets hit again, and you know, the odds of decrementing are even greater because it's times, you know, it'd be to the power of -1, it will be removed. So this still works for reading it, because if we go and read light, we see that the first 2 rows have 1s when we go to read it, but there's nothing in the 3rd row, and that's fine. We still get a count. Light's still in there. It still has a count of 1. And if we go to read object, we still find 3 values for object, but one of them is smaller now. But we take the biggest, and so it's still 2. So this is still accurate. It's still accurately reflecting the counts of the things in here. Heavy keepers tend to erode the value. So the count will never be bigger than it should be, but it will be low. It's often lower. And so it's actually really not reliable for counting, because as this fills up, those counts start getting whittled away at occasionally. And so they're not as reliable. But what it does is each time we modify that min heap, we get a new count, we shove that value onto the min heap, or we modify the heavy keeper, we shove the value onto the min heap. And that results in storing the top 5 in this case, most commonly used UFO sightings. Disk apparently is number 1, followed by sky. You can use top K in Redis. You call top K.reserve. You give it a number, which is the number of items you want. You give it a width, which is that width that we were showing there earlier of those arrays. Give it a depth, that'd be your number of hashes. And you give it a decay, which is the reciprocal of the number I gave you. So 1.05, the reciprocal of that would be 0.9 something. Here we're just specifying 0.9, but it does the same thing otherwise. To add things with top K, we just use top K add. We give it the key and we add disk. Here we're adding disk and teardrop, and here we're adding light, disk, and teardrop. So if you're paying attention, that's 3 disks, 2 teardrops, and 1 light. When we go to query it, we can say, is this in the top K or not? Top K.query. Is disk in the top K? Yes, it is. What's the count of teardrop? Top K.count will tell us that. Again, the count's not super reliable, but it's available if you want to use it. And top K.list will give you the 3 things that are in the top K. I think I might have time to run my demo. I will run the demo super quick. I built this is in Python, but I built a little app that tears through the words in UFO sightings, and it uses JavaScript to do that, and uses Python and some NLTK stuff and everything to do that. Let me see if I can find, there it is. We'll go ahead and start this up. I'm going to launch Redis. This would be the time that Docker decides to pull down a new version. And then we'll run, I've got app.py. I don't really have time to show you the code itself. But I've got a little Flask app in Python that basically runs the web app. And then the build will start parsing this big CSV file full of UFO sightings and pull the words out and shove them in here. And if we go to the app, we can see that these numbers are increasing. It's going through and finding the top 10 UFO shapes and the top 10 UFO words. So these are the top 10 most commonly used words in UFO sightings. Lights and light and are popular options. Object is also very popular. Sky, that makes sense. So this is my little demo. This is out on GitHub. You can go play with it if you like. I've got, I do have some Java code here as well. I did Minhash in Java. I've got Bloom filters written in C# and JavaScript. Minhash I did in Java, and JavaScript, and Top K I did in JavaScript. So you can go check out and play with some implementations of these algorithms. And that's my demo. Here's a bunch of resources to go check out. You want to check out the data set. It's at UFO Sightings. All these URLs are in the slides, which I have a link to next. I work for Redis Labs. Go check out our university and Discord server and stuff. And code and slides are at this QR code. I promise it will not send you to a Rick Astley video. You will not get rickrolled if you scan that QR code. It will take you to my GitHub. But if you don't believe me, just know that I'm never going to give you up and I'm never going to let you down. So that's my talk. We got time for questions, right? We got about
10 minutes.
About 5 minutes for questions. 10 minutes, and I ended that right at the 0-0 mark on the timer here that I'm looking at. So I'm kind of proud of myself there.
So amazing. Thank you for your talk. It was good. And we have questions. So could you please start from the very beginning? Could you please highlight well-known tools, libraries you are aware of which use probabilistic data structure internally, and more important, for what purposes? I know Cassandra used Bloom filter. Who else?
Well, I mean, of course, obviously Redis has these as well. I'm not really sure. A ton of places. I don't have a good answer to that question. But as far as particular uses for them, there's the general use case of I've got a lot of data, but I need it to be really fast. I don't have time to go tearing through all of this. I can't just do select star from users where username equals X when I have 10 million users. It's just inefficient. And I did not. There we go. That could have been way worse. Yeah. So there's sort of that general use case, right? Of I've got a bunch of data and I need it to be small. If you are dealing with any sort of big data scenario, these are the scenarios where these become useful. If I'm counting video watches, unique user watches on YouTube video, then hyperlog log will work because it will say you can just add the users to hyperlog log. It'll just tell you how many unique people viewed this thing, right? So it's those really large countings that you need to do, and where the accuracy isn't super important. The YouTube video count is a good example. Do I really need to know that it's exactly 1,037,000 views, or is it okay if it just says 1,030,000? That lack of accuracy is valuable in those scenarios.
Okay. That's all. Okay, thank you. That was my question also. So probabilistic data structure is deterministic data structure on steroid plus special algorithms that we run over it, or not?
Yeah, I think that's a fair summary of what a probabilistic data structure is. Because we have deterministic data structures internally, right? The heavy keeper is in and of itself deterministic, but when you combine it with the way we use it with hashes, it becomes probabilistic. Same thing with a Bloom filter. The array list or the list of the bit array we're using is just a bit array, right? But it's got an algorithm around it that changes its behavior. So we interact with it in particular ways. So I think that's a fair way of summarizing a probabilistic data structure. And it's almost always using hashing tricks. And lots of times your data gets lost. So you're taking your data, you're hashing it, and then you're storing the hashed results. And so like the heavy keeper doesn't have your keys in it anywhere. It has the hash and the count. And it's only pulling it back out. And it's using, when you say is object in there, it's really saying, I hashed this. Are these hash values in there with particular counts? And so your data is kind of gone.
So in our old school ML world, we, for example, have some classification model, and we have some result of the classification, which is, I don't know, archived as a list or as a tree or something like that. So in our modern world, we have it bounded as some probabilistic data structure, which does classification for us, for example, and use hashes for it or something else. Not classification, but classification is a buzzword.
Yeah.
Thank you.
Yeah.
So, and the last question, which papers, books would you suggest to read more on the topic?
I actually don't have a good book suggestion. My talk has, let me take it back here. I've got some links in my talk here. This is a lot of the resources that I use to help figure out some of the stuff. The Bloom filters by example is a fantastic example of a Bloom filter. And there's a tutorial on how Minhashes work. This is the white paper on Heavy Keeper, which it's a white paper, so it reads like a white paper. It's dense and full of mathematics, but it's accessible. So these are the resources I use to learn my way around these particular ones in depth, so that I could, mostly I just use them, right? But understanding how they work is interesting, and these are the resources I use in particular to get under the covers of these things. So I don't have a specific book recommendation, but that would actually be an interesting read. I've heard rumor of an interesting thing called stochastic data structures, which are really interesting from a mathematical point of view, but don't really have any practical application. And so I haven't really invested any time in learning how they work yet, because like, well, I can't really use them. There's not a ton of reason to understand how they work, other than just idle curiosity. So
Okay. Thank you.
So I got a couple questions that I didn't have solid answers for. Apologies. But
Okay.
That's where we're at.
Thank you. So we have only one task to do. So please select the best question, I think, from asked, and the winner will get the book from Manning Publications, Classic Computer Science Problems in Java. So
I'm going to go with the probabilistic data structures equals deterministic data structure plus special algorithm. I think that's I think that's a solid question. It's an insightful question because it shows that there's a comprehension of what's going on here, and then just looking for that validation. Okay. So I think that's a good question. So congratulations, you've won.
Okay. So that's it. Seems like that's it. Thank you for your talk. It was interesting. It was helpful.
Absolutely.
And see you on our chat. Maybe you can ask more questions to Guy. And
absolutely.
See you on the backstage. So thank you. Bye.
Bye.